Design of a Conscious Machine by P. Alan King. We define here the primary concepts needed to make a hardware machine with intelligence capabilities similar to animals and humans. A machine that unconsciously manages attention shifts, innately imitates actions of others, wonders what if, and then learns why. We propose a lightweight, minimal design which uses several well-known artificial intelligence techniques from connectionism and machine learning. Although the algorithms described here are known and realizable, they are also complex and require further development. Ahead is the construction of a software simulation environment, where the architectural definition will move closer to implementation. Brains constructed here will be tested first in simple environments, like the drunkard's walk, and then graduate to more complex worlds, like controlling the operations of a video game, and effectively being Mario in the land of Super Mario Bros. Section 1. Introduction. What is the essence of the functions that the mechanisms of our nerves and brains perform as we live our lives and try to do better? We seek functions that soak up the ways of the world like sponges and allow the being they control to prosper. How might these be implemented by cortical mini-columns as atoms of the cortex? As a starting point, we explore some massively parallel algorithms that might underlie these human-like effects. Our architecture is constructed of a synergetic combination of mechanisms, each of which embodies a familiar aspect of cognition, and together synergize interesting emergent elements. Why it should work this way is of less importance than how well the pieces actually perform together. The brain is the best existence proof of intelligence we have, and neurology provides a pathway to understand the brain's physical structure. The study of developmental stages of various species has heavily influenced this architecture. To keep combined explanations understandable, some very simple individual models have been used. They explain essential operation just enough to achieve the desired system's synergies, but avoid any undue complexity, just to mimic animal behavior. Engineering is useful in our work here too. This is, after all, the start of an engineering plan: to build a computational medium containing the hard parts of cognition, into which experience will naturally grow unaided. The design of large engineering projects, like large shared memory multiprocessors and routers, involves dozens of people. It is guided by an architectural document containing almost cartoon-like descriptions of the primitive operations available. Everything else is built from them, like a house from bricks. Our plan uses variants of the classical mechanisms of evolutionary computing, machine learning, and connectionism. From them we assemble our tentative straw man proposal, which will be cumulatively strengthened. A major milestone here is when all elements are assembled and in some level of communication. Section 2 describes how the being's worldly knowledge is held in a particular kind of element, and how that element works. Section 3 imagines a full-size system so constructed and describes its operation. Finally, some critical implementation choices are described in Section 4. Section 2. Functional Requirements. The functionality described at this level drives lower-level implementation choices. To create a being that will innately prosper. The architecture proposed here creates a computational environment rich in its support for modeling the world. Thus, we get closer to our goal of creating consciousness. We start by defining a computing element called a factal, to hold all pieces of the being's worldly knowledge. We assume that a factal represents just a single bit of information about the world, with more complex data types composed as conglomerations of factals. These are usually large and sparsely activated, and have some interesting properties. Thus, a factal maintains a single, particular one-bit predicate about the world. All information the being has about the current conditions of the world is held in the active state of its factals. All information about models of the world are held in the interconnecting patterns of those factals. Having this one form provides a major simplification in our core design, with more complex variables such as angles held as vectors of possible values. The functions of a factal include instantiation of new factals, constant estimation of the truth of the factal's fact in the being's perceived environment, managing desires that a factal's fact become true in the world, and planning ways of making it so, and digital memory storage. As an example, a factal might represent I am standing. As I stand, it becomes true and allows other behaviors like walking around. My desire to go somewhere else triggers my desire to stand, and I stand, if possible. We describe much of the functionality of factals by how groups of them operate together. From this, the functionality of individual factals must be determined. New factals are added to the machine to record newly explored parts of the being's enormous state space. Perhaps thousands of these must be born every second in a complex brain. We believe factals learn their identity at birth. This identity is chosen in such a way that every new factal automatically claims a unique piece of the information territory for itself. That identity is determined by how it is wired to other factals. Factals lie in a hierarchy of sophistication, where facts range from very simple on the bottom, near the sensors, to very highly sophisticated on the top. These match and isomorphically invert the process by which sensory information was generated in the world. There are several ways of encoding the estimate that a factal makes. One might encode the probability of truth, a value between 0 and 1. This probability is updated with Bayesian-like rules when information moves in the cortical data plane. A priori information is combined with new information to produce a posteriori information. It can encode the raw importance of a truth as its estimate. Thus, if two estimates compete, it is easy to choose the more important. It can encode the data types for belief networks of Judea-Pearl, which will probably be included in some form. It will also probably encode other strategies that involve force and averaging. The reenactment simulator described later will probably use one of these as its backbone. Section 2.1. Smaller factal groups. A worldly variable, or variable for short, encodes information which is best expressed as an enumerated range of possible values. For example, color may equal red, green, white, etc. It is implemented as a finite array of factals, one for each potential value. The range of a world variable may change occasionally after learning when a value factal might be added. Although a world variable may take on arbitrary estimates for its values, it is said to be well-behaved if statistically it has just one significantly active value at a time, or none if there is no information. Algorithms such as those of Jeff Hawkins work best if this is the case. Related aspects are groups of related variables that are known to all refer to the same underlying cause. Plants are groups of connected factals with common purpose and reward structure. Two interesting kinds of plants, situation trees and coincidence records, are described in Section 4. Gardens are evolutionary computing environments which support the growth of plants. Section 2.2. Cognitive functions. A factal has a physical manifestation which manages the operation of a fact in the cognitive mechanism being constructed. We also assume most or all mechanisms of a factal are in the same place. This might account for the neurological form of the mini-column. The functionality we believe that is required to animate a factal is fourfold: identification of new situations, world maintenance, including estimation and desirability, reenactment simulation, and long-term digital storage. To explain of their function, we resort to a metaphor called the forest, castle, journal, as shown in Figure 1. Although the description is metaphoric, precise algorithmic definitions are implied. There is an enchanted forest, and in the forest there is a magical castle, and in the castle there is a journal of all. The castle, as enlivened by the actions of its inhabitants, controls and manages the forest for the purpose of the castle. An example, to quarry granite or collect honey. The forest is thought of as analog, while the castle and journal are digital. The journal is thought of as software, while the castle and forest are hardware. The mechanisms of the castle are strong, functional correlates of consciousness. The journal holds the entire history of how the castle has interacted with the forest, including the distinctions used. It also contains a complete set of models of what happens in this forest. Castle inhabitants read the journal and then go into the forest and improve things. The journal is also indexed so that at any moment of time, the conditions of the castle's simulations are directed to predict the future of the forest. A particular area of the forest can be selected as the focus of the attention of the castle. When connected to a particular area, the castle observes and teaches the forest using supervised learning techniques. Without the castle's attention, things in the forest will continue on as best they can. In the machines with hierarchically composed data planes, global coordination of attention is difficult, but it turns out to be quite unnecessary. Section 2.3. Macrostructure of the whole cortex. The forest part of each fractal operates as a data flow machine, distributed cortex-wide. There is much internal structure to this data plane. Its layout must be done to keep wiring costs low. Serendipitously, segregating unrelated data into different cortical areas of preprocessing is a good practice. This segregation can be seen in the well-known Brodmann areas. The protocol binding the areas together into the data plane has several parts. It maintains consistent representations across the cortex of the current brain state, using data flow machines built from these related aspects, and processes associations as well. With the ability to extract causality and representations, fractals organize to, simplistically, detect lines in V1, two-dimensional objects in V2, motion and color in yet other visual areas, and so on. We here believe there are many further bidirectional filter layers above that, embodying the upper levels of our understanding. There are filters formed by all of our knowledge to the most sophisticated explanations we have of the world, passing through many cognitive areas such as the what-where paths and the remembered present of Gerald Edelman. All of the nuances we understand are held in this data plane. Section 3. Processing in an information domain. Figure 2 shows the processing of a domain in more detail. The various descriptive layers and languages for design are shown arrayed vertically. There are fractals, two kinds of brain states, and semantic networks. The information domain of a machine encompassing all of these layers is characterized by the information at its inputs. The processing shown in the figure is fractal, in that it applies to both very small information domains of under, say, a dozen inputs to very large brain-sized domains. Processing in small information domains should keep the units from exploding combinatorially, but still allow many layers of cascading. The being in the figure is experiencing a scene from Macbeth, as shown in a cartoon. A single fractal of many is shown in red. All information flow is bidirectional. A dedicated real-time area in the bottom contains a situation tree, action trees containing known behaviors, and low-level reactions between them. For example, stranger equals don't trust. Situation dynamically marks the being's cognitive information space, as cairns mark trails above the tree line. Where we are, amongst the cairns, can be evaluated at any time, presuming each estimates how close we are to it, and we can desire to be at a different cairn. Information for situation is determined at each level of the sophistication hierarchy in one of three ways: sensation, involves detecting causes based on the coincidences in lower-level, more sensory fractals. This is sometimes called spatial pooling. Modeling involves detecting causes based on coincidences between past and present to form a forward predictive model. This temporal pooling also helps recover hidden state. Expecting comes from higher, more global places in the hierarchy and bias the local choices. They focus attention and set learning contexts. Information from each of these may or may not be present at any one moment. They are combined by Bayesian methods in the data plane. Presence of redundant modalities fosters learning. An attentional mechanism can connect to various real-time areas of the forest. This is shown as a telescope, which can pan and zoom to various things we call zombies. Zombies are areas of the forest which do not currently have the attention of the consciousness. The attention mechanism feeds the reenactment simulator, a generative or forward model which predicts sensory information by mapping from causes to sensory consequences. It provides an internal model of the causal dependencies among states of the external world. We believe that to experience some phenomenon, one must first simulate it inside the brain. The reenactment simulator provides a single detailed analysis for a wide variety of patterns presented it. Descartes describes a similar element of consciousness, which Daniel Dennett names the Cartesian theater. Descartes falsely claims it was centralized. Many others, including Helmholtz, explore the central role of simulators in cognition. All this predates our modern in-depth understanding of computers. The simulation parameters are the highest level of the reenactment simulator and become part of the situation output. Sub-simulator configuration and their hierarchical typology can be serialized by language and then deserialized in the brain of another, effectively transferring a meme of fractals. The situation output is the final output of situation, which is very much like a generalized form of place cells. Limiting its values is important. Its elements are the basis for expressing every experience. The situation output is not well behaved and must be fed into a schema of coincidence records to form a unique brain state. A single fractal representation for every experienced pattern of the simulation output. It is built as a series of trees with shared leaves. These trees may also include internal analysis, attitudes, and actions associated with an experience. Many additional fractals may have to be added to encode each new experience, especially if it is novel. The semantic network has nodes which are unique brain states and links which indicate related states. The reenactment simulator can act as a write head, creating a tape as links recording past experiences. A list of the past nows form a history tape, a perfect linear history tape of the past. In partial summary, since all these pathways are bidirectional, it is possible to recall a particular brain state from a history tape and move it in the other direction, down through layers into the simulator. There it is reenacted in simulation and re-experienced. To try this out now, think of your first kiss. Hopefully, you've just recalled a brain state from a memory and re-experienced it. There is an organic network editing process which condenses meaning and morphs the linear tape into individual, separately usable models, which are then inserted into the operation of the reenactment simulator and the situation and action trees. The fractals of the semantic network also have links that are read by the reenactment simulator to guide it in the prediction of the future. Links have two ends to connect fractals. Links also have additional pointers to type and strength. Some link types carry truth estimates during situation to create the estimate of a fractal from its neighbors. Other types connect fractals of the semantic network, adding meaning by their presence. Section 3.1. Caveats. We have described a simple model of cognition, but there are still many critical details which must be added for this design to be used in scalable systems the size of the brain. What is missing includes adding continuous time, organic, not toy, encodings, decentralizing data, noisy data, world variables that are not well behaved, inaccuracy of efficient optimizations, seamless module boundaries, non-ideal situations, managing combinatorial explosions, detecting equivalent forms, limited fact instantiation rates, and distribution of centralized functions. Section 4. Implementation Notes. Implementations may take multiple incidents to learn. Implementations may use lossy information compression if it attempts to preserve meaning as much as possible. We believe that much of the robust nature of human thought is a synergetic byproduct of such mechanisms. Implementations may contain statistics on the number of occurrences akin to those of N-arm bandit processes to aid growth and culling. Section 4.1. The Modeling Strategy. The brain knows it has good models of the world if they're able to predict the future properly. We use many small models rather than one big model for two reasons. Model building algorithms generally scale supralinearly, with the number of inputs making big models is harder, and smaller models can be wired together differently in different situations, giving greater cognitive power to the simulation. A small model is shown in Figure 3. In it, the function g of z is the predicted value of a world variable u. It is computed using a tree. The tree acts as a dynamic decoder, switching experiences to the leaf that best characterizes the current z, and growing new leaves as new experiences enter. The estimate g of z is retrieved from selected leaf. The answer returns back to the same path to the trunk. When the result inaccurately predicts u, an error signal, x, is generated and the tree updated to accept blame. This might involve adjusting Stoller split thresholds, but commonly involves adding new branches to the culpable part of the tree to distinguish the new condition. New branches are usually chosen to be switched by the most active, unused dimension in the elements of Z. The conditions that cause the error are active in the path, and this makes updating easier. For delayed reinforcement, a mechanism to save and recall those conditions, as they were at the time the estimate was made, is required. Section 4.2. Coincidence records. Coincidence records are used to dynamically record all the particular sets of its inputs that have ever occurred together. Coincidence records are composable. It is possible to make new coincidence records from the outputs of several more detailed ones. Thus, the lower levels of coincidence trees tend to live scattered across sensory Brodmann areas, while various integration areas combine them in different ways. A schema of coincidence records is defined to generating a very large variable called the unique situation, which is well defined and has a single fractal representation of all patterns encountered in the situation output. A bidirectional coincidence record is shown in Figure 4, and although it only shows two of each, it can have many inputs and users, up to some implementation limit. The elements inside this bidirectional unit are actually unidirectional. In it, activating all the lower sensory inputs in the pattern activates the upper output. The names input and output are with respect to the sensory direction, shown here in red, going up the hierarchy. Companion expectation signals, shown in green, flow down the hierarchy. Activating the expectation of an upper output causes an expectation of the pattern to appear on the lower inputs. Coincidence records also have an output D that indicates its association is true but not expected. Other mechanisms monitor these unexpected signals during learning and construct minimal trees to contain them. A generalized form of this schema performs a weighted sum and threshold instead of the AND. By adjusting the threshold, it can reform fuzzy matches by using mid-threshold values and bidirectional OR. The OR is useful to declaring that all of its inputs are equivalent, hence decreases combinatorial explosions. Section 4.3, Hippocampal Routing. Evolution seems to have an insatiable desire for more associations beyond what we have shown with coincidence records. We propose the hippocampus performs a vital role in determining associations at the macroscopic level, where it acts like a castle in a central role closely akin to short-term memory. Figure 5 shows the system operation as follows. Absent prefilters and sharing, the current situation is fed directly to the hippocampus, which determines new associations. This theory does not require us knowing its exact function. The hippocampus can learn new associations quickly, but can only hold a limited number of them. Once an association has been learned, the hippocampus then transfers it to a much less expensive and more effective form as a cortical prefilter built from new axons and synapses. With the prefilter in place, the hippocampus no longer has indication of the association, freeing space for new associations to be learned. One can think of the hippocampus as a CPU cache, writing its data back to memory, the cortex. Learned associations are moved to the cortex as prefilters using a process I call Hebbian arborization. In it, axons are attracted to dendrite sites with which they co-fire. It operates using axonal growth cones, which are hypersensitive to the direction of signals that are coincident in time with their firing. This forms a Hebbian network which is much denser than classical Hebbian networks and operates by synapse growth rather than adjustment. The hippocampus repeatedly co-fires the coincident ports in a form of rehearsal, which dramatically accelerates the speed of Hebbian arborization. In our metaphor, this is the castle teaching the forest. The brain might have evolved this way if the computation required for learning new associations grows supralinearly but can be shared amongst groups of fractals. Event sharing is yet another way to significantly increase the number of potential associatable input signals by organizing them into mutually exclusive groups in advance. We imagine a concentration multiplexer in the entorhinal cortex which selects which group is active. In summary, we have described a simple model with significantly human characteristics. In it, algorithms to seek out causes have been postulated. Much more background is available at brain-gears.blogspot.com.